I'm Mark Barley, consultant anaesthetist in Nottingham, TIVA and processed EEG geek and honorary secretary of the Society for Intravenous Anaesthesia. And I hope the newcomers to Nottingham have all seen these fantastic new pumps that we've got. These are the Alaris Nexus pumps. These are the latest generation of BD pumps. We've got 250 of these, the largest rollout pretty much anywhere in the UK. A little bit of a delay in getting them to you because of COVID, stopped microprocessor development, but we've got them now. So I hope you've all seen them. But there's one thing I'm sure you have noticed, and that's when you turn it on, you are besieged by an array of different models nowadays. The models you know and love, and some new names on there as well. We've got Marsh, Schneider, Pediatric, Kataria, Eleveld, Matro, Minto, and Eleveld for Remifentanil as well. And there are a huge number of different TCI models available to us. Now, I know that some of you will be looking to do exams, and one of the things in the FRCA is that TIVA questions are unanimously badly answered, and we really can't be having that with Nottingham as the centre of excellence for TIVA. So I'm going to dive a little deeper and explain something about the different models that you might have heard about, which is going to hopefully emphasise why Eleveld is an enormous step forward. So here's lots of different TIVA models which have been derived over the last few years. Let's have a little look at some of these in detail. Now, the first thing to know is that Marsh, which you might all think of as quite an old TIVA model, actually involved no patient data at all. Marsh is actually a re-evaluation of a very small study done by HEPS back in 1987, just 18 patients, the majority of which were men. They were all relatively young for NUH standards, very slim for NUH standards, and had spinals and various other drugs. And they were all adults, of course. Schneider came along in 1998 and performed a human volunteer study. These were not patients. Schneider's study of 24 volunteers were all only given propofol, no co-medication at all, but he did use a slightly larger weight distribution, and some of them were quite tall. Now, the thing with TIVA models is that they work really well in the group of patients they were designed around. Unfortunately, working in 2023 in the UK, we don't have an awful lot of patients that are, first of all, human volunteers or correspond to the HEPS's original data. So the models that we have don't really fit with our patient cohort. And this can lead to a little bit of inaccuracy, and it can certainly lead to us having to fiddle with some of the numbers that we type into these pumps to work around some of their limitations, which we're mainly doing subconsciously, although we're going to dive into the detail in a few slides' time. One of the points I really want to make with all of this is that there has been an enormous change in the sophistication of pharmacokinetic modelling. So at the bottom left here, this is a computer for everyone who has been born in the last 25 years. This is what they used to look like. This is a very old computer running a TIVA model back in the late 1980s, and there's a syringe of propofol. As things have advanced in sophistication, so has pharmacokinetics. Our pumps nowadays can do vastly more just in the pump itself than the desktop computer back in the old days. So where does that leave us with Eleveld? Eleveld is a general purpose model. What does that mean? It means it's got good predictive performance for a wide range of patient groups and clinical conditions. It's going to simplify the decision of which model do I need to use? Do I need to use a pediatric model? Does my Kataria go down as lower age as my Pedfuser? What about the weight? Should I be using Cortinez's model because my patient's over 122 kilograms? What should I do? It's going to improve our ability to use TCI across the whole patient cohort. It's going to promote confidence in those people who are new to TIVA and have accuracy compared with specialist TIVA TCI models, which actually aren't available on our pumps anyway. So these general purpose models have wide applicability over age, various patient sizes and comorbidities. Eleveld is pharmacodynamically calibrated to the BIS index value. It needs less tweaking intraoperatively. You don't need to fiddle with the machine, and the dosing of drug that it delivers magically almost aligns with the SPC product insert for propofol. It gives what it should do. So I like to think of Eleveld as the Lord of the Rings model, because it's one model to rule them all. Now let's think a little bit more about TIVA and how these models are constructed and some of the limitations that we have with the Marsh and Schneider. So when a pharmacokinetic model is designed, you inject propofol and you measure the plasma concentration. And you do this tediously with either arterial or venous blood that's sampled frequently over the to generate a washout curve like this. You'll remember that we have a 3-compartment distribution of rapid, mainly into the vascular compartment, intermediate into well-perfused organs, muscles, and slow, which is thought of as redistribution into fat. But really, and if you remember the primary, I remember learning how to write all these little equations out to try to understand how the different compartments were constructed. Now, this is dead easy to create an algorithm to calculate a pharmacokinetic profile if you're just looking at one patient. But the more patients you look at, the more complicated this becomes. And the whole purpose of a TCI model is to be able to cope with the varying different sizes and shapes of patients that we have. So we can produce this mammalian 3-compartment model and stimulate what's happening to our propofol. How much do we need to give as a bolus to fill the central compartment to produce a rapid onset of brain effect? And how is that propofol going to redistribute to different body compartments and finally be eliminated? Let's wind our mind back to Heps and Marsh's model. This used a linear scale for these central compartments. This means that as you get bigger, all of your compartments get bigger. As though somebody who weighs 100 kilograms magically has twice the plasma concentration of plasma volume, fat volume, or V2 than somebody who weighs 50 kilograms. And that clearly can't be the case. We don't double in size as our mass increases. And this produces some of the limitations with very obese people using Marsh, where induction doses can be very, very large indeed. Schneider came along and thought he'd use a few other parameters. If we remember, Marsh only uses weight as a variable, doesn't use anything else at all. The age is only entered to ensure that your patient is over 16. You could type 17 or 70. It makes no difference to the rates of infusion or the bolus that's delivered. Schneider came along and had a bit more of a powerful computer system and was able to evaluate and discover that in his modelling at least, that weight, age, height and sex were all useful covariates. And these boxes here show all the different parts of the 3-compartment model that are influenced by those covariables. It's important to remember that sex is really just part of this James equation for lean body mass. And this is one of the limitations, I think, of Schneider's model, is how it's tied to lean body mass. Now, a couple of other interesting observations. It doesn't matter how big you are, but your central compartment is the same size, whether you're 50 kilograms or 150 kilograms with Schneider. Your fixed volume is 4.27 litres. That's why you might notice that Schneider gives quite a small bolus. That's why you're all used to dialing up a fairly high number, 4, 5 or 6, to achieve induction with Schneider, because the calculations in that model seem to fit with his volunteers having fairly small central compartment. And really the big adjuster to the size of bolus you get comes from your elimination, how it's predicted how quickly you're going to get rid of that bolus, which modifies the initial size. Age plays a role, and that was one of the nice things about Schneider, is it was one of the first models that took into account as you got older, your muscle mass would change, for instance, and you were less good at eliminating drug, obviously. Now, the big problem that we have with Schneider, of course, is in obese patients, where James's equation that calculates lean body mass starts to fall apart. So we have to put this into context, though, that James's equation came out in an era when there weren't quite so many people of quite the size that we see nowadays. This was never a model that was designed for obese patients, and James's equation was never designed for obese patients. What happens, and where this falls apart, is if you're very short but very, very fat, your lean body mass can actually start to become negative when using James's equation. What you'll have noticed is the pumps actually limit the maximum BMI that you can type in to try to limit that. The problem being that if your lean body mass becomes negative, a weird quirk of the equation is that that elimination value becomes really, really high. And then that calculates an absolutely massive induction dose, which would be quite a profound overdose for patients. So we use a BMI limitation in any patient that's over a BMI of 35 for a woman and 42 for a man with Schneider. And unfortunately, of course, many of our patients weigh outside of those limits these days. So Eleveld took all of this information thinking, where can I improve on current TCI models? And he worked with the University of Groningen with the names in TIVA TCI, Tony Absalom, Cortinez, who'd done the bariatric model, and Michael Struze. So these are the big names. If you're going to have an A team of TIVA, these are the guys you want on the job. And what Eleveld did was use the Open TCI project, which is essentially a repository of all of the TIVA data from all of the key pharmacokinetic studies. So that's 30 studies, 1,033 patients, 11,000 individual data points of propofol concentration. These are patients weighing between 680 grams up to 160 kilograms, and from 27 weeks of age up to 88 years of age. So this is covering pretty much the entirety of our normal practice. And using his pharmacokinetic monitoring mathematics, used these different variables: weight, postmenstrual age, height, sex, and concomitant drugs, which is very interesting. We'll talk about that in a little bit of a moment. And these are data sets that cover volunteers, patients, arterial or venous blood, all sorts of different ages, all sorts of different weights. We've got patients with cirrhosis, we've got patients who are alcoholics, we've even got Doofus's redhead study, which I don't know an awful lot about. I think it speaks for itself, that we're looking at a very broad patient population. The ones that we're used to, as I've already mentioned, small groups, mixes of patients, volunteers, of fairly limited ranges. So by combining masses of data across multiple different groups, we can produce a much more accurate model, which is going to be broadly applicable. Now, of course, a child and an adult, or a neonate and an adult, or a neonate and an obese adult can't be just scaled linearly. So Eleveld got very, very smart and used a principle called allometric scaling. And what allometric scaling is it's a set of theories that allow scientists to understand the relationships between small organisms and large organisms. So, for example, a mouse heart beats very, very fast, doesn't live very long. Elephant, enormous, heart rate very low, lives for ages. And back in the late 1940s, people became aware that animals all had different energy requirements, and they're able to plot graphs like this, looking at animals' metabolism, comparing the mouse, who might eat 120 calories a day, through to an elephant that would eat somewhere in the region of 5, 6, 7, 10,000 calories a day. And they discovered a relationship that, despite the different size, nutritional intake, that their metabolism and body compartments scaled at a factor of around about 0.75. So we couldn't use the linear scaling that Marsh had used. We needed to use a different parameter. So I'm going to just bamboozle you by showing you Eleveld's model. And here it is. This is the detail behind it. And I want to point out just a few little quirks. And that this gives me the same feeling as when I look at this as that terrible FRCA revision book from back in the day that said, question, derive the Henderson-Hasselbalch equation. I was like, oh my gosh. Now, we're just going to look at this to look at some principles, not because of any of the detail and the quirks. But what I want to show you is that the Eleveld model is sophisticated enough to take into account the maturation of a neonate through into an infant. So up to around about 5 to 6 months old, a maturation function kicks in, which takes into account the different clearance in the maturing child. We've got that scaling 0.75 factor used here in the calculation of clearance and how propofol moves between compartment 1 to 2 and from compartment 1 to 3. We've got the Al-Salimi fat-free mass calculation, which is useful in calculating that weight-based or fat-based compartment. So we're seeing a real level of sophistication here. And I want to draw your attention to these red boxes where the presence of additional analgesia is taken into account. And I'm going to touch on that in a few moments' time. So how do we use it? So obviously, when we first turn on the pumps, we get the option to use the adult or the pediatric data set at the moment. So at the moment, of course, you've got Kataria, Pedifuser, and Eleveld on the pediatric side, and on the adult, we've got Marsh, Schneider, and Eleveld for adults. We get the screen that says choose mode. Now, this is new. We didn't used to have this. If you press TIVA, that's going to give you mils an hour. All the dosing is in mils an hour. It'll show you what the effect site concentration or plasma concentration is, but you're controlling the mils an hour. The pump will make no decisions. It'll just do what you tell it. You type in 20 mils an hour, it'll give you 20 mils an hour. That's where you'll find this straightforward mils an hour infusion rate for all your other infusions. What we want is TCI, target controlled infusion. We set the effect site, the pump chooses the rate and will decrement for us. We come to our lovely list of models, of which I'll touch upon at the end. I'd like to see a lot less on there for obvious reasons. Then some of the defaults have changed a little bit. I've selected Eleveld here. Our height defaults to about 180. You put the age in, of course. The height defaults to 180. It used to be 170. Then you're going to see a weight, and this weight will differ depending on what the height you've typed in. This is well, I was going to say a gimmick. It is a gimmick that BD have put in. And what BD have decided here is that they're going to give you a weight, a starting weight, that's 50%, is on the 50th centile of all of the weights of a patient of that height. So this is the average weight for a 180 centimetre patient having propofol in Eleveld's model. So it's a better starting point than just starting with 17, you're having to increase always. We get to this screen that says opioids in use and defaults as yes, and I'm going to touch on that in the next slide. Leave that as yes. Then we have this screen here that allows us to slow down the infusion rate if we wanted to from 1200 mils an hour to make it something slower. And then the most important screen, and this is our sense check. This has always been there, but I think we often just press confirm and skip through it. But what this screen does is it's showing us what our, with an effect site concentration of 1, this is going to deliver our patient a 4 ml bolus and then run an infusion after a pause of just under 20 mils an hour. And what you can do on this screen is dial up your chosen induction profile and sense check, do the numbers look right? Doesn't matter what model you use, this has always been there, but I use this as a sense check to make sure I'm going to give something that's going to be pharmacodynamically acceptable. Now, what is the deal with opioids? Why does Eleveld even mention it? Well, patients in TCI studies are, well, they're not volunteers, so they're not well. They've got comorbidities. They've had neuroaxial blocks, regional blocks, opiates, clonidine, all sorts of different things that the models haven't historically corrected for. The volunteer studies like Schneider have only had propofol. And what Eleveld noted is that all the volunteers, which are the dark dots, have a very different distribution of pharmacokinetic characteristics than the patients. So the patients are in the little crosses, the dark dots are our volunteer-based studies. And it was felt that the difference between these pharmacokinetic characteristics reflected the other drugs, that having remifentanil actually alters the clearance of propofol. Of course, it drops your heart rate a little bit, vasodilation perhaps, interferes with hepatic metabolism, depending on the block or drug that you've been given. So that parameter about opioids is there to correct for the volunteers not having had any other drugs, which is actually rather clever. No other system does that. So how are we going to choose what our induction dose is going to be? Well, one does not simply just use the same numbers as Schneider. Remember what we said, that Schneider's got this fixed central compartment and lacks all of the sophistication of our wonderful Eleveld model. So if I were to just do my normal thing with our 81 kilogram female patient and just dial up 5 of Schneider and press go, I'd give 11 mils, which is very reasonable. That's what I expect to see if I was running a concomitant remifentanil infusion. That would be fine for induction. I'd then drop onto an infusion of 124 mils an hour for maintenance. But if I did that with Eleveld, remember we said that Eleveld's very sophisticated in how it calculates central compartment, I'd get a really large bolus. And that probably would be more than I needed to induce this patient. But you'll notice the infusion rate is considerably lower. So Eleveld did a very clever thing and took all of the studies that had correlated BIS index values with plasma concentrations of propofol and came up with this dosing graph. And this shows you the amount of propofol that you need to administer, the effect site concentration you need to program in to achieve a particular effect. And that effect is 50% drop in your BIS index value. He found all the studies he looked at, the mean starting value on the BIS was 93. So to drop it down to 47, 50% BIS effect, all you need to do is find your patient's age, read up to the anaesthesia line. If they're 40 years old, you dial in 3. That's all you need to do. You press go, the magic happens. The patient will get a modest bolus and then drop down onto their infusion rate. We can even just choose a 10% BIS effect, drop the BIS down to 80, 84 for a bit of sedation. In that 40-year-old, we're dialing in 0.9 or 1. The graph makes it very, very easy to relate the pharmacodynamics to the pharmacokinetics. Here's a patient we just looked at where we compared the Schneider and the Eleveld using my 5 value of what I might normally do in theatre. Here we are, she's 50. We go up to the line. It's going to be 2.7 on the graph here. I program that into Schneider's model. I get this teeny weeny little bolus that will probably not touch the sides particularly, and then a 67 mil infusion. If I use Eleveld, here we are, much more reasonable bolus, and then a sensible maintenance rate that again is lower than Schneider's. So Eleveld's going to give you a larger bolus, but a lower infusion rate. You don't need to overshoot and overpressure like you may have had to do with Schneider in the past, working up to 5 or 6 and then dropping down to 3.2, 2.8, wherever you might be. And what you're going to find when we compare to other models, let's look at Marsh here, adult, 35 years old within the Marsh parameters, that over time, Schneider's actually at an hour going to give you a bit less propofol. So it's not about the mass of drug, it's about how it's delivered. Larger bolus up front and then a slightly lower maintenance infusion. In the elderly, using Schneider's model, which is age corrected, as we mentioned earlier, we'll see exactly the same. Slightly larger bolus, but over time, we're giving slightly less propofol. And this is all pharmacodynamically linked. In the obese patient, we give very much less propofol than Courtinez's model, which was specifically designed for obese patients, but using a smaller data set. If we think about what the SPC tells us to do and how we should dose our drugs, this is all of the patient's induction dose over a range of different ages. And these green boxes show us what the packet would tell us to do for different age ranges of patients. So we see a good relationship within the pediatric and the elderly patients between the SPC and what Eleveld's suggesting that we do. At all different ages, using the Eleveld model, we're able to track the BIS with pretty good accuracy across most ages there, and that we can see that there's a very clear relationship between a reduction in effect target and age as patients become increasingly old. Now, there's been validation studies done. The validation studies, about 160 patients from 3 to 90 something, I think, have demonstrated some very sensible real world usage that shows that that effect target correlates with that little graph I showed you across the age range. Colleagues often using a little bit more propofol in the patients in their mid-60s. And the range really of all propofol delivered is between 80% of predicted effect site all the way up to about 140% there or thereabouts. There's always going to be individual variability. And with the time course, this is the time course of an operation, 100 being do what the graph tells you to do. You can see that people often start at 100. They might go up just a little bit to cover laryngoscopy or insertion of a laryngeal mask airway or first incision, but then they drop back down to where the model suggested they needed to be in the first place. This little graph here around BIS monitors, responses to BIS monitoring is very interesting. This is where we want our patients to be. You can see that when the BIS numbers go low, people are reducing the target, as you might expect them to. When the BIS numbers are sneaking up above 60, you can see people are increasing the propofol. So they're actually individualizing their dosing to the effect sites and pharmacodynamic responses. Now, of course, we've pushed the limits in Nottingham, as we always would do. I had a patient a couple of weeks ago for airway surgery with a BMI of 60 who weighed 176 kilograms. And this is outside of what the model will let us deliver. And this is partly because of a limitation put in by BD rather than from the Eleveld's model itself. But we could only go up to 152 kilograms on the Eleveld propofol and 102 for her height on the Remifentanil model. However, we have got pharmacodynamic calibration. We must always be using our processed EEG monitors whenever we're using TIVA, and we can see that we can get down to that magic 47 with ease. So with Eleveld, we've got one model to rule them all, suitable for hobbits, elves, dwarves, wizards, and humans, but not orcs. Orcs get desflurane. In summary, Eleveld simplifies TIVA. The typical dosing range at induction would be 2 for a frail elderly patient to 4 for a pediatric patient. There are fewer pump interactions required. We'd always want to use that lower effect site concentration in our older patients, or even consider just working up 1, 2, 2.5, 3, whatever you might prefer, and pharmacodynamically calibrating. And it does align with the SPC as well. I've not mentioned Remifentanil. The construction of the Remifentanil algorithm is very, very similar to propofol, and using it within 3 to 4 nanograms of Remifentanil is what's recommended at the induction stage, and then titration to clinical signs. So Remifentanil is similarly robust, works across age ranges and into bariatric patients as well. Quick plug now. The best TIVA meeting you'll ever go to will be CIVA 2023 up in Glasgow in November. I'll be there, Dr. Blanks will be there, Dr. Noah will be there, a great Nottingham contingent flying the flag for TIVA and processed EEG across the UK and beyond. Now, we're going to hand over to Tom, who's going to talk to us about paediatric experience with Eleveld's model.
So, yeah, thank you very much, Mark. Now, I would call this the real highlight of the ACE meeting, talking about pediatric TIVA, of course, and the new kid on the block. So I'll drop in a little bit of science. not too much, and then we'll have a chat about some of the practical, or what the impact of that science means practically for those of you using pediatric total intravenous anesthesia or dabbling your toes into it. So it won't be a surprise to anyone who's even sort of gone near anaesthetizing a child that they need a larger amount of hypnotic or anesthetic agents to induce loss of consciousness, sedation, or anesthesia. And this has been, conclusively demonstrated time and time again with all sorts of different agents. If you're a volatile fan, there again is the evidence saying that you need a higher partial pressure of volatile agents to induce anesthesia. Lots of these studies, I should mention, don't comment on the premature cohort, particularly where your max significantly or your anesthetic requirements significantly reduce. But we won't get too deep into that because it's probably starting to get a little bit into the weeds. So our models, our TCI models, need to take that into account. And one of the sort of ways that we take this, a lot of the models that we use are not included on the right side here, but PEDFuser and Kataria are two of our older models that we've become relatively well used to using. And just to highlight something that Mark has already brought out, and we'll go into more detail in just a bit, the Eleveld model delivers a much larger initial bolus. That's particularly true in pediatrics. If, like me, when I first started using it, you're very used to PEDFuser targeting plasma concentration rather than effect site concentration. And one of the other areas that we're hoping PEDFuser, or sorry, the transition to Eleveld will help us with, this is a bit of I hope it comes out okay. At the top there, this is a chart demonstrating something called the predictive error, percentage predictive error of a model. And you can hopefully make out that here on top, PEDFuser has a negative predictive error that compounds over time. What that means is that gradually, and the x-axis is in minutes, so 122 hours, 4 hours onwards, over the course of a long case, what you think you are delivering, so for example, a plasma concentration of 4 miles per mil, for sake of argument, your real, your in vivo plasma concentration will gradually be falling away from that. And for those of us who do long cases, or for those of you who've done transfers, I know Jake Turner has mentioned this to me a couple of times, what you can find is that gradually over a long case or a long transfer, you'll be increasing your total, your amount of your targeted plasma concentration on the pump to maintain the same process EEG or physiological variables indicating depth of anesthesia. What you're not really doing then is you're not really increasing the in vivo target, but you're instead trying to catch up from the tail off that you get with this negative predictive error. And Eleveld, again, hopefully you can appreciate, maybe, I hope it comes out okay. Eleveld has a less negative predictive error. So I haven't done enough long cases with Eleveld yet to conclusively say, oh, I'm definitely doing it less. But theoretically, we should be required to top up our infusion concentration on a less frequent basis when we transitioning from Eleveld to PEDFuser. So combined with all the bits that Mark has told us already and the stuff that we know now, when moving from PEDFuser to Eleveld for kids, what practical differences do we need to take into account? Well, the first one I've put at the top there is that we're measuring, of course, effect site concentration, not plasma site concentration. And that's a relatively minor practical difference for the sake of documentation, but not for the sake of the impact on the patient, because as Mark has alluded to, we need to reduce our effect site target compared to PEDFuser. And this has caught me out, I'm embarrassed to say, on quite a few occasions. So you will have a dramatically increased bolus size if you keep the same targets that you would normally be targeting with PEDFuser. Sonia mentioned in the comments, the impact of sort of one pump or single syringing. So this is relatively common within pediatric anesthesia. It's to add an amount of remifentanil or an amount of alfentanil to your syringe of propofol, which delivers a very stable and well-suited delivery of anesthesia for short day case procedures. But one of the benefits of it is that it's very easy to maintain spontaneous ventilating in patients, unless you're aware, unless you do what I did and go way too deep when transitioning from Eleveld to Pediatric. I had some quite protracted apneic phases up on my E39 day case list. So you need to be particularly aware, Sonia, if you're dealt with your one pumping, single syringing, whatever you call it, you want to make sure you have a much slower or much lower effect site concentration target as opposed to using Pediatric. And Abby mentioned something in the comments about the sort of impact on the larger bolus size on hemodynamics. I think that's really, really important to take into account. So I sort of alluded to it here, particularly small children. You recall that small children can't adjust their left ventricular end diastolic volume, so their cardiac output is proportionate to their heart rate. Propofol is a fascinating agent, but it interferes with your afferent signaling to your cardio accelerator centers and therefore prevents children or anyone from mounting a tachycardic response to the negative ionotropine and peripheral vasodilatation that propofol induces. So in very small children or very unwell children, you can reduce their stroke volume by giving them an agent that's directly negatively inotropic. You can worsen any relative hypovolemia by inducing peripheral vasodilatation. And then you stop the child, or propofol stops the child, from mounting a tachycardia response to that. So I think we do need to be relatively careful in small children or unwell children, particularly as we get used to it. Moving off that, you will notice the loss of consciousness is more rapid. I've definitely noticed that, which is depending on the type of anesthetic you're delivering to or how happy your kid is. Is that a good or a bad thing, I guess? Normally a good thing in my hands. And again, as I've alluded to, we should theoretically need to increase propofol less during long cases. One of the sort of local factors to take into account is that our pediatric ward nurses are not, it's not well embedded yet to measure height as well. It's getting better, and they are meant to measure height as well. You might find that you maybe need to remind people to get a height done preoperatively. I'd definitely say at the moment, I'd say it's probably pretty patchy at the moment. Just demonstrating, I promise Mark and I didn't cheat and show our presentations to each other beforehand. This is just giving you a sort of a rough idea, exactly as Mark alludes to, the sort of rough numbers that you should be aiming for a 5-year-old. And then you can sort of extrapolate beyond that. So looking to have a sort of a bit of a roundabout 40, consistent with anesthesia, you want to be dialing up to about 4 mics per mil. And then to prove as well that Mark and I are absolute nerds of a feather, much like my friend Bilbo here, he says, why shouldn't I keep it? But that joke didn't work because that would be for Pediatric, so I blocked out the, so why should I keep it, or why should you move to Eleveld or for our pediatric cases? Well, first of all, as Mark has alluded to, unification of models. So it has, as I say, validated from 27 weeks post-menstrual age and from 680 grams all the way up, which is certainly very new to us. Pediatric bottoms out at 5 kilos. Kataria, I don't know why I'd use that, but if you were, it bottoms out at 15 kilos. So it gives us a much broader range of patients we can deliver validated TCI models to. It does take into account the pharmacodynamic interactions of propofol and opioids. I would have a slight word of caution just around in using high-dose remifentanil. Now, these aren't my words, but I'm told that the remifentanil calculation is relatively simple, which clearly not for a mere mortal like me, but if you're very deep into TCI algorithm design, probably very, very simple. And it's modeled on what's called typical low-dose opioid anesthesia. I'm going to be honest and say I don't know exactly what that means, but there's a mention in an editorial to have some sort of caution with high-dose remifentanil. And then thirdly and finally, why I think we should move to Eleveld, is that we're widening the demographic of the data. It's an area I'm very passionate about. PEDFuser is derived from the Marsh data set, which was in males, and believe it or not, not everyone is a Caucasian man. So I think it's really important. We know that being female you need a higher amount of anesthetic delivered as a child. So it can only be a good thing to widen, I think, the demographic of the data you provide. So that brings me just under time. Any questions at all?